All right, so we are on to Bode plots. We've just finished up talking about frequency response, doing some examples, and we're going to get into Bode plots, which are basically just another way to represent the same exact data that we've already been plotting, right? So back here, we were looking at frequency response for an RL circuit. Here we actually determined what are the values of the magnitude and the phase at different frequencies, and we're about to do the exact same thing. So let's go back real quick and just look at the RC circuit frequency response that we saw previously, right? So this is what we saw when we did the RC circuit example. We saw this plot right here, which basically shows that at low frequencies, I get my output to be equal to my input. At high frequencies, I get my output to be 0. And at intermediate frequencies, I get this response, right? And so what we're going to do is we're going to look at that exact same data, but we're going to look at it a little bit differently. And that's all that a Bode plot is. It's a different way to represent this data. It's only slightly different. So let's go ahead and take a look. I just wanted to bring our minds back to that RC circuit response because this is what we're going to look at now. So for the time being, don't look at this bottom plot. Let's just look at the top one right here. This is the exact same plot that we've already seen, right? This is the RC circuit frequency response. We see again that at low frequencies, right here, my output's equal to my input, or 1 volt. And right now I finally plotted V out over V in because all this time I've been plotting the output voltage. So the units on this y-axis here were volts. Now they're actually just unitless because it's the ratio of V out to V in. So you see now that the ratio of V out to V in is 1 at low frequencies, just like we saw before. The ratio of V out to V in is 0 at high frequencies, just like we saw before. And similarly, the cutoff frequency, or the 0.707, which is going to happen like right around here, is still right at around 159 hertz, right? However, this plot on the bottom, it definitely looks different, but I want to assure you that this is the exact same data. It describes the exact same circuit. The only difference is take note of the y-axis, okay? This is called decibels, or dBs, right? I have that written right here. The difference between these two plots, the exact same data, right? The phase is the exact same. I'm still going 0 to -90, 0 to -90. You can see that the phase plot looks identical in both cases, right? It's the exact same phase. The only difference is that the magnitude is no longer plotted like on a linear axis. Okay, these dBs, or decibels, are a logarithmic unit. And you might be like, why in the world do we need to introduce logarithms? Well, the reason that we do is because putting things in terms of dBs actually makes our lives a whole lot easier when it gets to more complicated circuits. The RC circuit is probably not a great example. Obviously, it's very simple, and it's a good example for that reason. But because it's so simple, you can't really see the benefit of why we want to use dBs in a plot like this, because this plot doesn't look much more complicated than this one here. But when you get to much more complicated circuits that have several inductors and several capacitors, and you need to analyze all the different things that are happening at different frequencies, Bode plots are the way to go. Okay, so Bode plots are the industry standard. This is how you will see any plot for frequency response in a data sheet, for a part, for basically anything that you're going to do in electrical engineering. You're never going to see it in terms of linear. I like to introduce it in terms of linear to get the concept across. Basically, this linear axis here is showing us that, you know, between this tick mark and this tick mark, I have 0.1. Between this tick mark and this tick mark, I have 0.1, and so on. That's what's called a linear axis, right? It's the equal distance between tick marks. In dBs, that is not the case. It's a logarithmic unit similar to our x-axis here, which is also logarithmic, right? Between 1 and 10, I have a factor of 10, right? 10 divided by 1 is 10. Between 1 and 100, I have the same factor of 10, right? 100 divided by 10 is 10. 1,000 divided by 100 is 10. And so instead of having the same difference, I have the same ratio between tick marks, right? This is 2 hertz, this is 20 hertz. This is 300 hertz, this is 3 kilohertz. So that's the difference between logarithmic and linear axes. Now, dBs look different, and that there's a reason for that. And later on in the video, we're going to, or it's not in this video, but in another video, we're going to go ahead and we're gonna derive why we use the dB, what that unit is, what it's telling us, and why this plot looks different from this plot. But for now, just take note that the only difference between the frequency response that we've already been doing and the Bode plot is that this y-axis for the magnitude is plotted in dBs instead of plotted in a linear y-axis, okay? So let's move on to this really quickly, the key characteristics of the Bode plot. Of course, the x-axis is logarithmic. We've already seen that, right? We said that the same ratio between tick marks rather than the same difference. We saw that that's the same case with the stuff we've already been doing up to this point. We were already using the logarithmic x-axis. What the new piece here is that the y-axis for magnitude is plotted in dBs or decibels, okay? So again, dBs are decibels. I'll just write that out, decibels. So you've probably heard of decibels in terms of sound or volume. There's a reason for that as well. And I wanted to point this out so that I can introduce the concept of the Bode plot. And we're gonna basically go through these two things so that we can get a better understanding of the Bode plot. I'm first gonna do a review of logarithms and logarithmic functions and logarithmic axes. And then I'm going to do a little bit of an overview of where the dB unit comes from and why we use it. And then once we're done with that, we're gonna move on into the Bode plot, characteristics of the Bode plot and transfer functions, and then we'll get further along into doing some examples and actually analyzing Bode plots and sketching some Bode plots, similarly to what we've already been doing, but in this new way with this dB y-axis, which is the industry standard for this kind of thing, for frequency response. Okay, so I'm gonna go ahead and end this video. I think it's probably gotten a little bit long, and in the next video, I'm gonna start reviewing logarithms. Okay, so I'm gonna end this video here.